Welcome back, AP Chemistry students, to Unit 4 Chemical Reactions. Today we'll be talking about Unit 4.5 Redox Reactions. Now we've talked about the other two types of chemical reactions according to the AP exam, those being precipitation reactions and acid-base reactions, and we briefly introduced reduction and oxidation reactions, but this subject requires a little bit more explaining. So redox reactions are when atoms gain or lose electrons to develop a charge or oxidation state. And in first year chem, as well as in some previous units, we did some general oxidation states. We said, group 1 metals are always +1, alkali earth metals are always +2, halides are always -1, chalcogens are always -2, nitrogen and phosphorus are always -3, and then the transition metals, we said, had a wide range of charges, and I didn't ask you to memorize them with the exception of 3, those being silver, zinc, and aluminum. And I told you as long as you kept these straight, you'd be fine. Well, it's time to expand on that knowledge. It is true that group 1 and 2 metals always form a +1 or +2 oxidation state respectively. And it is true that silver, zinc, and aluminum will always have a +1, +2, or +3 oxidation state when in a compound. However, the nonmetals can have some weird oxidation states. The polyatomic ion chlorate exists. Chlorate forms between chlorine and oxygen molecules. However, if oxide is always -2 and chloride is always -1, how are these atoms attracted to one another? Well, it has to do with varying their oxidation state. So the oxidation state or oxidation number, there are some rules to it. Again, alkali earth and alkali metals will always be +1 and +2. Silver, zinc, and aluminum are always +1, +2, and +3. But after that, the nonmetals, their oxidation states can fluctuate with a couple of exceptions. First off, oxide is always -2 with a rare occurrence of peroxide, and fluorine becoming fluoride is always -1. Other than that, the sum of all the oxidation numbers or charges within a species has to be 0 unless it's an ion, in which case it must be charged. And anything elemental, we say, has an oxidation state of 0. Which brings us to example 21. We are asked to determine the oxidation state of each atom in each compound. So the first one being nitrogen. Nitrogen is elemental. There's only one capital letter present, and since this is the only thing present, we would assign it the oxidation state of 0, that it has no charge, because as a compound it has to have a charge of nothing. So the oxidation state of nitrogen in the nitrogen molecule is 0. In carbon tetrafluoride, these 5 atoms are attracted to one another based on their oxidation state. Fluoride is always a -1. So by having 4 of them, overall, fluoride is providing us a -4 charge. Overall, this compound is neutral, however, there is no charge, so the charge of carbon, therefore, must have been +4, because a +4 and a -4 would equal 0. In sulfuric acid, each oxygen has to have provided us a -2 charge. So by having 4 of them, we have an overall charge of -8. Now, when everything is said and done, all of these oxidation states have to equal 0. Two hydrogens. Hydrogen is a group 1 metal. Hydrogen, therefore, we are going to say is a +1. So 2 of them would be a +2. So something +2 minus 8 has to equal 0. Well, sulfur must have been a +6. Now, up to now, everything we have talked about has been neutral, meaning the overall charge had to equal 0. In dichromate, we have a polyatomic ion. By being a polyatomic ion, that means that when everything is done that's not going to equal 0 this time, it has to equal a -2. Again, each oxygen is always -2 by having 7 of them. That gives us an overall charge of -14. 2 chromiums -14 has to give us a -2. So something -14 equals -2, that must be 12. So 2 times something has to equal a +12. Chromium must have been a +6. Now, you might have noticed something a little bizarre in that last example. I wrote +6 instead of 6+, unlike some of the others when I've written 2-. The direction of positive or negative can go in front of or behind an oxidation state. You will not be marked off for either one. If you are taking this class at another school, I would suggest you ask your professor what they are looking for specifically. Some professors are very specific in that oxidation states have their direction stated after, and some professors are very specific that have come before. I personally do not care as long as you state if something is positive or negative. Determining the oxidation state of an atom or a species within a compound is a good multiple choice question. However, sometimes we will use this to break a reaction into 2 halves. When I have the single replacement reaction between aluminum and copper nitrate, where aluminum nitrate is formed and elemental copper is produced, this reaction has 2 halves, depending on which side you're looking at. Are you looking at the aluminum, in which case aluminum goes from having an oxidation state of 0 to being the ion, aluminum +3, or are you looking at the copper, where copper goes from being an ion to being elemental? So this reaction technically has 2 halves. We could break it into its half reactions. Half reactions are actually what powers a battery. We separate a reaction into the 2 parts that occur, and the transfer of electrons we capture with a wire, and that's what powers, say, your cell phone or a light bulb, or maybe the computer you are looking at. So you need to be able to understand and write half reactions. In a half reaction, we are going to separate the oxidation and reduction halves, because if something is reduced, something had to be oxidized. If something lost electrons, those electrons have to go somewhere. So for example, if we had the redox reaction when chlorine gas is bubbled through bromic acid, the chlorine will replace the bromine and give us bromine gas and hydrochloric acid. This reaction has 2 halves. The hydrogen doesn't change. Hydrogen's in a compound in both cases. Hydrogen's always a +1, so hydrogen is really a spectator ion here. What's occurring is bromide becomes bromine, goes from an oxidation state of -1 to 0, while chlorine becomes chloride, an oxidation state of 0 to -1. So this reaction actually has 2 half reactions. One in which bromine loses an electron, A loss of electrons is oxidation, while chlorine gains that electron. So chlorine is reduced. It goes from being 0 to -1. The only way it could do that is by gaining an electron. So the two half reactions here could be seen as bromide becomes bromine by losing an electron. Chlorine becomes chloride by gaining that electron. If you give off electrons, a loss of electrons is oxidation. A reduction is a gain. So here is the two half reactions for the reaction between hydrobromic acid and chlorine gas. Notice that the reaction is still balanced, and the reaction, if you lose 2 electrons, those electrons have to be picked up by the other side. So half reactions should always align with one another. The oxidation giving off 2 electrons means reduction has to accept those 2 electrons. So the two should equal one another. So if something is oxidized, it is going to force something else to be reduced. That's why we call whatever is oxidized a reducing agent. A reducing agent is a thing that forces something else to be oxidized. An oxidizing agent is something that forces something else to be reduced. So when I see the word agent, if a question says, what is the oxidizing agent in this reaction, or what is the reducing agent, I always think of spies. A double agent plays for the other side. So when I see the word reducing agent, I scratch through it and I write the opposite. I'm looking for what is oxidized. Or if I see what is the oxidizing agent, I scratch through it and I say, all right, Professor, you're looking for the reduced. What was reduced? And as long as you know those vocabulary words, you're safe. So, on page 30 of your packet, you'll find practice on determining the oxidation state. Now, in these problems, the vast majority of them are not asking for every single player in the compound. They are looking for specific ones. So this first one, you are only looking for the carbons. And the next one, you are only looking for the bromides. Go ahead and pause the video and complete page 30 in your packet. All cards on the table. That will be the end of Unit 4.4 in terms of the AP exam. You are no longer going to be asked to balance reactions by half reactions, which is what this next segment is. However, I still use free responses that have these types of questions in them, so if you are going for a 5, this does not hurt to know. Balancing, remember, means what you start with has to equal what you end with. There is another method to balancing besides just looking at the mass. You can look at the redox reactions, the two half reactions, and balance those. Balancing redox reactions is a process. There are steps. And you get used to doing those steps the more you do them, just like balancing. Now, redox reactions typically happen in solution where there is an excess amount of water. So when we balance redox reactions, we are going to be adding water wherever we need it. There will be some acid-base chemistry involved because just like in first year chem, there's not a clear-cut separation of types of reactions. In AP Chem, there is not a clear-cut separation between redox reactions and acid-base reactions. So we will follow these 9 steps in order to balance this reaction. Permanganate and iron 2 make manganese 2 ions and iron 3. The first thing we need to do is break this reaction into the 2 half reactions. So permanganate is the only place that the manganese ion could come from, so that is 1 half reaction. So I'm going to write permanganate becomes manganese. The other half reaction has to be the other player. Iron 2 has to have become iron 3. first step in balancing a half reaction is to balance by mass of everything except for hydrogen or oxygen. So that just means make sure that you have the same number of each element. Let's do the easy balancing first. 1 manganese makes 1 manganese. This first reaction is balanced. 1 iron makes 1 iron. This second one is as well. Now we balance oxygen by adding water. This reaction has to happen in water, so that means we can add water to either side so that it works out. The 4 oxygens from our permanganate had to have made 4 waters. Iron 2 becoming iron 3, there's no oxygen to balance. Next, balance hydrogen by adding hydrogen ions. In water, water naturally will break down into hydrogen and hydroxide ions, just at a very small ratio. So in all water, we can add hydrogen or hydroxide ions as needed. So since I have 8 hydrogens in a product for this first half reaction, I will add 8 hydrogen ions to my reactants. We don't need to do that with the second one. So next, we will balance the charge. On each side of the reaction, the charges have to be the same. So the overall charge in the reactants of my first half reaction is a +8 and a -1 for an overall charge of +7. The products have an overall charge of 0 and a +2, so an overall charge of a +2. In order to balance the charge, we will add electrons, which means we can always bring numbers down. It's very difficult to bring numbers up. So with a +7 to a +2, I can bring +7 down by adding 5 electrons. That will recalculate this. A -1, a +8, and a -5 gives us a +2 for our charges. So this reaction is now balanced. There's a conservation of energy. Our second half reaction, iron 2 becomes iron 3. Obviously these are not the same, so I will have to add 1 electron. A +3 and a -1 gives us a +2. This is now balanced by charge. Now, the 2 reactions occur simultaneously, which means they need to be the same. If this reaction needs 5 electrons, those electrons have to be provided by my second half reaction. So this reaction needs to be 5 times as bigger to provide me the 5 electrons needed by my redox reaction. So I'll multiply my oxidation of iron by 5. 5 times 1 is 5, 5 times 1 is 5, 5 times 1 is 5. The reaction is still balanced, and now it aligns with my reduction. Lastly, we're going to push these all together and cancel out like terms. 5 electrons plus 8 hydrogen ions plus the permanganate ion plus 5 iron 2s gives us 5 iron 3s, manganese, and 4 waters. Once you've combined the 2 reactions together, you cancel out like terms, meaning if something's in the reactants and products, you are going to cancel them out. Again, think of products as negative and reactants as positive, so they cancel one another out. Plus 5 electrons and minus 5 electrons are going to cancel one another out. Other than that, we have no other like terms, so the balanced reaction here is that 8 hydrogen ions, the permanganate ion, and 5 iron 2s produce 5 iron 3s, the manganese ion, and 4 waters. Now, I will grant you, balancing by half reactions is by no means faster than balancing by mass. However, it is just one more trick to know. So let's do another one. Here again, we see the permanganate ion producing manganese, and this time iodide produces iodine. We start again by breaking it into our half reactions. The only place manganese could come from is the permanganate ion. So I'll start with those 2 species. Iodide must become iodine. The first thing you do is balance the masses. With the exception of hydrogen or oxygen, 1 manganese becomes 1 manganese. An iodide cannot become 2 iodines, so we must put a 2 here. After that, we balance oxygens with waters. 4 oxygens have to be used up to make 4 waters. We don't have that problem in our iodide half reaction. Balance hydrogens with hydrogen ions. 4 waters would need 8 hydrogen ions, and again, there's no hydrogen in our iodide half reaction. Next, balance the charge. A positive 8 and a minus 1 is a positive 7. A positive 2 and a 0 is a positive 2. So again, we will need 5 electrons to bring these both down to a plus 2. A minus 2 becomes a 0. The only way that could happen is if it gave off 2 electrons. And with our charges balanced, we now have 2 half reactions that need to equal one another. Again, meaning make the number of electrons the same. Nothing times 2 gives me 5, and nothing times 5 gives me 2, but 2 and 5 both have 10 in common, so I'll multiply this first half reaction by 2, and the second one by 5. And now that our electrons are the same, we can combine our 2 reactions. 10 iodides plus 16 hydrogens plus 2 permanganates gives us 5 iodines plus 2 manganese plus 8 waters. And we now have a balanced reaction. Alright, let's do one that's in a basic medium and one that's a little more complicated. Silver cyanide and oxygen gas make silver cyanide complex ions. Now, silver and cyanide both make silver cyanide, so they must be one reaction. So who's the other player in the game? It must be the oxygen. So what does oxygen have to become? Well, we don't really have anything there, so let's leave it for right now. Let's just do what we normally do. Balance everything except for hydrogen and oxygen. So silver cyanide becomes silver 2 cyanide, so we need 2 cyanides. Now for the second one, we don't have anything besides hydrogen and oxygen, so we're just going to move on. Balance hydrogen or balance oxygen by adding water. So there's no oxygens in our first reaction. However, here we have oxygen. It must have become 2 waters. Balance hydrogens by adding hydrogen ions. Again, silver cyanide has no hydrogens in it. However, our 2 waters would need 4 hydrogen ions. Next, we balance the charge by adding electrons. We have a -2 that becomes a -1. The only way it could do that is if it lost 1 electron. We have a 0 that comes from a +4. The only way that could happen is if it picked up 4 electrons. Once we have our electrons, again, they have to be the same. So this first reaction, this oxidation, has to give up 4 electrons in order for our reduction to gain those 4 electrons. So we're going to multiply this whole first reaction by 4. So 4 silvers, 8 cyanides makes 4 silver cyanides and 4 electrons. Those 4 electrons are picked up by the 4 hydrogen ions to make the water. Now that our 2 half reactions balance one another, that 4 electrons are picked up from the 4 electrons that are oxidized, our reaction is balanced in an acidic medium. So we can combine our 2 reactions. Oxygen and 4 hydrogens produce 2 waters. Here's our combined reaction in an acidic medium. However, the reaction tells us that it is supposed to be in a basic medium, which means we need to neutralize these 4 hydrogen ions by adding an equal number of hydroxide ions. Now, just like in math, what you do on one side of the equation, you have to do on the other. So if I add 4 hydroxide reactants, I have to have 4 hydroxide products. And those 4 hydroxides react with our 4 hydrogens to give us 4 waters. Now, with all of that said and done, we need to double check to make sure we don't need to remove anything that's on both sides of the reaction. Like, for example, we have water in a reactant and water in a product. So 2 waters are going to cancel out 2 of the 4 that we have here, giving us 2 waters and oxygen, and 4 silvers and 8 cyanides make 4 silver cyanides and 4 hydroxides. Our reaction should still be balanced, and sure enough, 4 hydrogens make 4 hydrogens. 2 plus 2 is 4 oxygens, make 4 oxygens. 4 silvers make 4 silvers. 8 cyanides make 8 cyanides. Our reaction is balanced in a basic medium. Again, balancing by half reactions is a very advanced concept and one that I do not foresee you seeing on the AP exam, but forewarned is forearmed. And with that being said, we are now done with Unit 4. We will have 2 labs in this unit that you may have started or you may start next class. But after that, you will have your test. So please begin your personal progress check if you have not already, and I will see you in Unit 5 Kinetics.